Welcome to another module in this massive open online course. So, we are looking at DSB, that is double sideband modulation with suppressed carrier DSB SC. Okay, so let us continue our discussion on DSB SC modulation. Correct? We have said this is basically your double sideband and SC stands for suppressed carrier. Okay. Let us draw the schematic of a DSB-SC signal of the DSB-SC. We have looked at the DSB-SC scheme. In a DSB-SC, the modulated signal xt is given as AC, that is your AC mt cosine 2 pi fct. There is no pure AC mt cosine 2 pi fct, that is the pure, there is no transmission of a pure carrier signal. This xt at the receiver is fed to a demodulator, correct. Alright, this is your xt, incoming message signal xt, or let me write it as AC mt cosine 2 pi fct. This is the incoming signal, this is the demodulating signal, right, that is cosine 2 pi fct, and the output is passed through a low pass filter LPF or low pass filter, the output is passed through a low pass filter which is cutoff frequency W, correct. This is your low pass filter, that is the response of the low pass filter, 1 between minus W to W and 0 otherwise, and the cutoff frequency W is chosen such that, well, Fc is much greater than W is much greater than Fm, and this is possible because Fc is much greater than Fm, and the output of this signal is therefore given of this LPF is given as half ACMT, where now we have recovered our message signal, where we have recovered our message signal MT. Okay, so this is basically the schematic diagram. Let me label this thing. This is your schematic diagram. So what is this? This is your schematic diagram of DSB-SC demodulation of the DSB-SC demodulation process. All right, this is a schematic diagram of the demodulator of a DSB-SC system, that is double sideband suppressed carrier. Now, in this module, let us look at another interesting aspect. Now, if you look at this, there is something interesting here, and you will realize that the success of this demodulation process or the efficiency, or we will look at in other words also one of the things that we have implicitly assumed without making too much of a fuss or without specifying exactly how this is done, what we have assumed is that these two cosine waves, that is your cosine wave, that is the modulating the carrier, that is the carrier wave, the carrier of the incoming signal, let us, that is the AC mt cosine 2 pi fct, and the demodel, the carrier, that is the carrier generated at the so we can call this as the carrier in message incoming signal the carrier of the incoming signal, correct, in input signal, let us input signal, which is basically, or carrier in received signal, let us put it that way, the carrier in the received signal, and this is the carrier, locally generated carrier at the receiver. This is the locally generated, is a copy of the locally generated what we realized is in the demodulation process, we need a copy of the carrier, that is cosine 2 pi FCT, which is locally generated, and of course, the incoming signal is modulated on this carrier cosine 2 pi FCT. Now, what we have assumed is that basically this, now of course, one thing is the carrier frequency is known, right, this is the carrier frequency on which the signal is being transmitted is known, all right. So, we can generate a local copy of the carrier at the receiver. However, what we have also assumed, and I have not explicitly pointed this out, is that this phase of this incoming, that is the phase of the carrier in the incoming signal and the phase of the carrier of the locally generated, what we have assumed is that these two phases we have assumed here, and you will see that we have assumed that these phases are equal, and you will realize that the success of this system depends on this fact, that is the phase of the carrier in the incoming signal, right, in the incoming signal at the receiver, and the phase of the carrier at the locally generated, phase of the locally generated carrier are actually equal, or in other words, there is no phase offset of the locally generated carrier with respect to the carrier wave component in the incoming signal. This is what we have implicitly assumed, right, and this is a very big assumption, as I am going to demonstrate later, correct. So, and this is termed as, when these phases are equal, this is termed as coherent demodulation. So, what is coherent demodulation? So, we have two, we have incoming message signal x equals AC cosine 2 pi, or AC MT, I am sorry, AC MT cosine 2 pi FCT, correct. This is your incoming signal or received signal, one can also say, that is probably clear, received signal. Correct, and we have the carrier, that is cosine 2 pi FCT, correct. We are multiplying, demodulating this with the carrier, this is the locally generated carrier, the locally generating meaning locally generated at receiver, and we have assumed that no phase offset that no phase offset between carrier wave in incoming signal and locally generated, that is we have assumed there is no phase offset between carrier wave in incoming signal and the locally generated, between carrier wave in incoming signal and the locally generated carrier, and this is termed as coherent demodulation. Coherent, let me just write it in bold letters, coherent demodulation, or basically synchronous demodulation. Coherence means that is in line, alright, something is, coherence means, coherence basically indicates that the carrier at the receiver is in sync or is in tune with the carrier wave of the incoming signal. They are coherent, alright. There is coherence, which means that basically something is in line or something is in sync, correct. And this is also termed as synchronous demodulation. This is also termed as synchronous. Another way is, probably even a better term is synchronous. Coherent demodulation or synchronous demodulation, which means both the same thing, that there is no phase offset between the carrier wave in the incoming signal and the carrier wave, that is the carrier that is locally generated by the oscillator at the receiver, correct. Now, in general there can be a mismatch between the phase of the incoming carrier, that is there can the phase of the incoming the carrier wave in the incoming signal and the phase of the locally generated signal. Alright, there can be a phase mismatch. This is termed as a carrier phase offset. Okay. So, let us take a look at this. In general, we have xt equals AC MT cosine 2 pi FCT and cosine 2 pi FCT plus phi. So, this is your incoming signal, correct. Once again, this is your incoming signal and this is the carrier, locally generated carrier generated at the receiver, and now you can see the carrier generated at the receiver or the carrier employed for demodulation at the receiver has a phase offset. Now, you can see there is a phase offset of phi. So, there is a phase offset of phi. So, the carrier at the demodulator is offset with respect to the carrier wave in the incoming signal, right, is offset by a factor of by phi, right. This is termed as a carrier phase offset. Okay, this factor phi is termed as the carrier phase offset. Carrier phase offset, this is termed as a carrier phase offset, okay, the carrier phase offset, and therefore, now the carrier generated at the receiver is no longer coherent, alright, it is no longer coherent or no longer synchronous with respect to the carrier wave in the incoming signal. So, the carrier wave at the receiver is no longer synchronized, alright, is no longer coherent or is no longer synchronized with the carrier wave in the incoming signal. Therefore, in this scenario what we can see, there is a carrier phase offset phi not equal to 0 implies carrier at local oscillator or carrier at receiver or local oscillator or your local oscillator is not coherent carrier of incoming coherent with respect to carrier of incoming signal. Alright, so there is non-coherence. Alright, it is not synchronous. The carrier generated at the receiver is not coherent with respect to the carrier wave in the incoming signal. Now, what problems does this lead to? Let us examine that. Now, let us examine non-coherent demodulation. We have xt multiplied by, remember our demodulation process. Our demodulation process is simply we take, as you can see from here, what we have is we have xt multiplied by cosine 2 pi f c t. So, for our demodulation process, what we employ, what we do is to simply take the received signal xt, multiply it by cosine 2 pi f c t, which is basically your signal ACMT cosine, sorry, now there is a phase offset of phi ACMT cosine 2 pi FCT times cosine 2 pi FCT plus phi, which I can write as, well, ACMT divided by, that is half ACMT times well, cosine 2 pi FCT cosine 2 pi FCT phi, that is cosine A cosine B, or twice cosine A cosine B is cosine A minus B, that is cosine phi, plus cosine A plus cosine A plus B, that is cosine 4 pi FCT plus phi. Now, you can see this component, this is the component at 2 FC, okay, and this is of course a constant. So, this is a baseband component, this is your baseband. This gives rise to the baseband component. So, therefore, what we have, or probably we have, I think probably I can write one more step, half AC MT cosine phi plus half AC MT cosine 4 pi FCT plus phi, and of course, this is the baseband and this is your component at 2 FC. Now, when we low pass filter this, you take this, pass it through low pass filter, again the same thing, cutoff W greater than, that is cutoff W greater than FM and W less than FC minus FM, correct. Cutoff is such that basically your W, or basically 2 FC minus FM, correct, 2 FC minus FM, okay, and we get, what we get is half, well, AC mt, correct, cosine phi. And now what you see is that you have this additional factor, of phi. You have this additional factor of phi which was previously absent in the case of coherent demodulation. Additional factor of phi previously absent in coherent demodulation. Okay, so now we have this additional factor of phi which was previously absent. And now you can see there is a problem because this factor of phi results in the power. Now if you can look at this, what is the power of the received signal? Power not of received signal, power of demodulated signal, the power of demodulated signal is 1 by 4 AC square the power of the message signal into cosine square of phi. So, there is a factor of cosine square phi, and remember cosine square phi is less than or equal to 1 implies the power is less than or equal to 1 by 4 AC square PM, which is the power in the coherent demodulation. So, the power is suppressed, or the output power of the demodulated signal is suppressed by a factor of cosine square phi. So, output power decreases by a factor of cosine square phi, which is basically less than or equal to 1. In fact, for phi equal to pi by 2, cosine square phi equal to 0. In fact, if the phase difference phi is pi by 2, that is a locally generated carrier is pi by 2 out of phase with respect to the carrier wave in incoming signal, the output power is 0 once you low pass filter it, right. The output power, which is basically proportional to cosine square phi, is 0, or basically the carrier at the locally generated carrier is completely out of sync, correct. So, the power it is orthogonal to the carrier wave in the incoming. This means, in fact, if you can see, this means carrier wave, locally generated carrier is orthogonal to carrier wave in incoming signal. The locally generated carrier is orthogonal to the carrier wave in the incoming signal, and therefore, the carrier wave this basically when it is orthogonal, right, when it is orthogonal therefore what is happening is basically once you demodulate with this orthogonal, because which is orthogonal locally generated carrier at the receiver, which is out of phase by pi by 2 with respect to the carrier wave in the incoming signal, and low pass filter it, the output power is simply 0, and therefore now you can see. And now for all values of phi between 0 and pi by 2, you basically have the carrier, the power of the output signal, which decreases slowly. So, for 0, right, when phi is equal to 0, you have maximum power of the signal at the output of the low pass filter. When phi equal to pi by 2, the the power, that is the power of the demodulated signal, is basically 0, and therefore, for values of phi between 0 to pi by 2, the output power decreases from the full output power, the maximum possible output power, to 0, and therefore, as phi, what you can see is as phi increases or as the carrier phase offset increases, right, the degradation worsens, all right, the received output power, the output power at the power of the demodulated signal progressively decreases, correct, the performance progressively worsens. As carrier phase offset increases, carrier phase offset phi increases, the output power of the output demodulated signal progressively decreases, and the performance, all right, progressively worsens. Okay, so that is something that we have to note. As phi increases, the output power of the demodulated signal, as phi increases, output power of the demodulated signal decreases, therefore, performance of receiver progressively worsens. Performance of the receiver progressively worsens as the carrier phase offset increases. Therefore, it is important to maintain this phase synchronization, right. Therefore, important to maintain phase coherence or phase synchronization with respect to the carrier at the receiver, correct. Therefore, it is important to maintain phase synchronization or phase coherence with respect to carrier in incoming signal, carrier wave in incoming signal. Okay. So, therefore, what we have seen, so in this module what we have seen is we have examined the impact of the carrier phase offset, of the offset in the locally generated carrier, correct, at the receiver. What happens when it is used for demodulation, when the carrier, that locally generated carrier that is used for demodulation at the DSB receiver has an offset with respect to the carrier wave in the incoming signal. We have seen that as the carrier phase offset, we have modeled this carrier phase offset, and we have demonstrated that as the carrier phase offset increases, right, as the carrier phase offset increases, the output power of the demodulated signal progressively decreases. Therefore, the performance of the system, right, as the output power progressively decreases, the performance of the receiver or the performance of the communication system becomes progressively worse. All right. So, we will stop here and continue with other aspects in the subsequent modules. Thank you.